Hello everyone, welcome to my channel and welcome to yet another video on integration. In this video I have one integral that I would like us to work on. It's the integral of 2x plus 3 in brackets dx all over 4x squared plus 4x plus 5. The approach is as follows. Let's look at the denominator. If you differentiate the denominator, you're going to get 8x plus 4, but we have 2x plus 3 in the numerator, which means we have to turn this somehow into 8x plus 4. And therefore it requires us to multiply, as you can see here, it requires us to multiply by 4, so we can get 8x here, but here it will be 12. So we'll see how we manipulate from there. But I don't want to change this, so I'm going to have to divide. I multiply by 4 in the numerator and I divide by 4 at the same time, so that we don't change the integral, as follows. So we have page 1, we have the integral of 2x plus 3 in brackets dx. We're dividing this by 4x squared plus 4x plus 5. So what I was saying is this is equal to 1/4 of the integral of 4 2x plus 3 dx all over 4x squared plus 4x plus 5. Now notice that these 4's can cancel. You're back to the original integral, but I'm going to have to expand in the numerator there. So we have 1/4 times the integral of 8x plus 12, and we have dx all over 4x squared plus 4x plus 5. Now notice something here. We need 8x plus 4, so which means I have to split this 12. I have to split this 12 as follows. So this is 1/4 of the integral of 8x plus 4, and then I have to say plus 8. We're dividing this by 4x squared plus 4x plus 5, and then I'm going to have dx over here. Now I'm going to perform term-wise division here, keeping 1/4 out. I'm going to divide this expression into 8x plus 4 and then into 8 as follows. So we have 1/4 the integral of 8x plus 4, divide this by 4x squared plus 4x plus 5, and then I have to say plus because there's a plus sign here. 8 all over 4x squared plus 4x plus 5, like so, and then we have dx outside like that. Now after this, what do we do? Well, what we do now is to distribute. I can keep the quarter out, but distribute the integral and the dx as follows. So this is going to be 1/4. Let me put a bracket out here now. The integral of 8x plus 4 all over 4x squared plus 4x plus 5, and then I'm going to say dx plus the integral of 8 all over 4x squared plus 4x plus 5, then I have to say dx like that. Right, now, so we have two integrals to work on. This is easier to work on. This one requires some work. So what I'm going to say is, moving forward, now all I have to do is to distribute the quarter, because we need to perform some tricks there now. So I'm going to say this is our page 2. So I'm going to say this is 1/4, distribute across, times the integral of 8x plus 4 all over 4x squared plus 4x plus 5 dx, and I'm going to say plus 1/4 of the integral of 8 all over 4x squared plus 4x plus 5, and then dx like that. Now watch something here. This part here is easier to evaluate. So I'm going to work on this first. I'm going to say let u be equal to 4x squared plus 4x plus 5, and then I differentiate this. du dx, you'll agree with me that this is going to be 8x plus 4. And then I'm going to have to multiply by dx both sides. So du will be equal to, open brackets, 8x plus 4, and then I'm going to say dx. And yes, rewriting this integral here, you'll agree with me that this is a quarter of the integral. Allow me to put 1 all over 4x squared plus 4x plus 5, and then I'm going to say times, open brackets, 8x plus 4, and then I'm going to say dx plus that integral there, this part here, I'm going to let it be equal to, I can keep a quarter out, and just say 1/4 I. We're going to have to work out what I is in the second part of this integration process. So let me remove that and say this part only, this part here, let it be equal to I. So I'm going to have that. But this one here is easy to work out. As you can see that now I can say this is a quarter of the integral of 1 over u, because that's u up over here, and then times this part here, you can agree with me that it's du, then plus a quarter I. We're going to work out what I is. This, you'll agree with me that this is just a quarter of the natural log of u, and then I'm going to have to say plus a quarter I. Now, we will come back and, perform the revert to our original variable at the end when we're done with the second part. Now we have to work on this integral now. So now the second part is, let's go to page 3 now. The second part is going to be this part here. We have to work out what I is. Evaluate this integral. 8 over 4x squared plus 4x plus 5 dx. So I equals the integral of 8 all over 4x squared plus 4x plus 5 dx. Now, if you look at the denominator, differentiating this, it gives us 8x plus 4. We don't have that expression in the numerator. So when that happens, there's something else that we need to do. What we need to do, first of all, take 8 out. So we have 8 times the integral of 1 all over 4x squared plus 4x plus 5 dx. Now I'm going to have to complete, because this is a quadratic expression, I'm going to have to complete the denominator, complete the square of the denominator, and therefore I leave the 5 out momentarily, and I'm going to say 4x squared plus 4x plus k, some constant k, can be written as a square of a bracketed expression. So what are we saying? What is the square root of 4x squared? The answer is 2x plus some constant a. So I'm going to have to expand the right hand side. Expanding this, you'll agree with me that is 4x squared plus this times itself, that's the expression. This times that times 2, so that's plus 4ax and then plus a squared. This is equal to 4x squared plus 4x plus k. Now watch, this part equals that part. And therefore here I'm going to take the coefficient of x equal to coefficient of x. So 4a equals 4. What is a equal to? 1. Right. And then I'm going to take the last part. Constant equals constant. So what do we have now? What we have is the following. K equals a squared. Bring 1 this side. So k will be equal to 1 squared. And the answer is 1. That tells you that for this to be a perfect square, all we have to add is 1 at the end there, then it becomes this expression. Now, so therefore, coming back here, we're going to rewrite this as 8 times the integral of 1 all over, watch this, 4x squared plus 4x plus 1. Why am I saying that? Because we have to add 1 there so that it can be expressed that way. But we have 5 out here, so we have to put 4 there. Fantastic. So now, don't forget dx there. Continuing, this will be 8 times the integral of 1 all over. Watch how I write this one now. I'm going to write it in that form, 2x plus 1, and I say squared. 2x plus 1, and I say all squared, but there's a 4 outside there, so plus 4. And then I say dx. Fantastic. Now at this stage, remember when you have something squared like this, tan substitution comes in mind, but there has to be a 1 here, so I'm going to have to force factorize this. So we have 8 times the integral of 1 all over, watch this, common factor is 4. 4 into this part is going to be 2x plus 1 all squared all over 4 plus 1, like that, and then dx. This 4 is dividing, remember, so it can divide into 8, and we have 2 times the integral of 1 all over this part here. This part, you can rewrite it as 2x plus 1 all over 2, and then we say the whole thing squared plus 1. You agree with me? If you expand this, it's going to be that expression. The numerator will be 2x plus 1 squared. The denominator is going to be 2 squared, which will be 4. Now, when I look at this part here, I can rewrite it, by the way. I can simplify that expression inside the brackets as follows. If I can squeeze it in here, it will be 2 times the integral of 1 all over. Divide in there, it will be x plus half. And we say squared plus 1 dx. You say, what did you do there? I did term-wise division. Divide 2 into 2x, the answer is x. 2 into 1, answer is half, but we have to square that. Fantastic. Now we can perform our tan substitution. Moving forward to page 4. Page 4. Now we're going to say, this is the expression we're going to say now. You can see it. Yeah. So I'm going to say, at this point, I'm going to say, let tan theta be equal to, watch this, x plus half. And therefore, from here, you can agree with me that we can perform what you call differentiation implicitly on both sides. If I may, you may allow me to be quick. I'm going to say sec squared theta d theta. The right hand side will just be dx. Now that integral then changes to 2 times the integral of 1 over tan squared theta plus 1 times, instead of dx, I'm going to put sec squared theta d theta. You'll agree with me that tan squared plus 1 is actually sec squared. So this is 2 times 1, the integral of 1 over sec squared theta times sec squared theta d theta, and these cancel. So what do we have? We have 2 times the integral of 1 d theta, and you'll agree with me that this is 2 theta. I can't say plus c because remember, we're evaluating I. But now what is theta? Well, at this point here, you can clearly see that from here, you can solve for theta and say theta is just going to be tan inverse of x plus half. So this then simplifies to 2 tan inverse of x plus half. What is this? Don't forget, this is I over here. That's our I. That's how it simplifies to. Now, we're going back to where? We're going back to here. Remember, it's a quarter natural log of u plus a quarter I. So we're going to say, I'm just going to do this and we'll summarize on the next page. So this will be 2 tan inverse. Sorry, I must have this one first. I must have a quarter natural log of u first. I think I must, yeah, I'm going to just write it here. So this is equal to 1/4 natural log of u, that part, and then I'm going to say plus a quarter, open brackets, 2 tan inverse of, luckily here we have our x already. We're just going to have to change that. So we have x plus half, and then now I must say plus c. But we must get rid of this u here, taking us to our final page. So moving to our final page, which is page 5. Page 5, we're now going to say that is equal to 1/4 natural log of, what is u? Well, going back to page 1, I think page 1, On page 1, if you would recall, actually page 2, here is u, this expression here. That's our u. Now, so we must take this expression and put it in that place. We take this expression 4x squared plus 4x plus 5 into that place. The question is, are we going to maintain the absolute value signs there? The answer is we will not maintain that. We're now going to say like this, 4x squared plus 4x plus 5. I'm going to show you why that is the case. We're closing that bracket and we're saying, remember, this is where we're at. A quarter natural log of u, that's the one. And then we're going to say these two here, you can see that that cancels that into 2 because that's 4. So 2 into 4, that's 2. So now we have plus half of tan inverse of x plus half, and then we're saying plus c. Let's rewrite this. 2, I just want to make sure that it looks better. 4x squared plus 4x plus 5 plus half tan inverse of x plus half, and then plus c. Now, let me explain to you why we must drop the absolute value signs. Remember here we did this completing the square process. We said 4x squared plus 4x plus 1 is a perfect square, and therefore this can be written as 2x plus 1. Remember a is equal to 1. A equals 1 here. Of course, a and k are the same because you square 1, you get 1. So this is what we're getting. But if you look at this expression here, there's a plus 5 here. So which means for me, we're basically saying therefore 4x squared, check this, 4x squared plus 4x plus 1 plus 4. The answer, I'm adding 4 now because I need a 5 there. This will be equal to this expression, which is this part, is equal to 2x plus 1 all squared plus 4. Remember, this part here is that part there, but I'm adding a 4. And if you look at this expression, it can never be negative for whatever value of x you choose. So this one here is actually, to be very strict, we can say that one is totally absolutely greater than 0 for all real values of x. It's positive for all real values of x, and therefore no need for us to use absolute value signs there. All right, so this would be our final solution to our integral. Looking very innocent, but you can see the processes involved. We've had to do a little trick at the beginning to let me take you to page 1. Page 1 must be here. We had to do something on page 1 over here to transform this, reduce it a little bit, so that we have something that can be evaluated by simple u-substitution, and then the other part required us to